Okay, so like I said, the exhaustive search to find the optimal decoder table looks to be exponentially complex in n and k, and there is a slightly simpler method, like I said, which uses this is a syndrome decoder. It's a slightly interesting idea. The complexity is 2 power n minus k, and for small examples it's interesting, and even for larger examples it provides ideas for suboptimal decoding. Okay, so that is the main point of the syndrome decoder. Okay, and it crucially depends on the parity check matrix, and it turns out using the parity check matrix for decoding is a far better idea in practice. Okay, so almost all the good codes that is decoded using the parity check matrix only. Okay, all right. So what is the idea here? So what did we see was the optimal decoder. So we wanted to do this operation, right? So we wanted to do argument minimization u in C, the Hamming distance between R and U. Okay, so this is the idea behind the optimal decoder. So notice R is C plus E, you can write it as C plus E. Okay, so we know R. Okay, so given R, we have been trying to find the best possible C. Okay, so notice the prior probabilities for C is equally likely to be any one of the 2 power k possible code words. Okay, you do not have any bias in the possible values for C ahead of time, you have no idea. Okay, and you have to guess all the possibilities if you are guessing C directly. On the other hand, what is totally equivalent is, instead of finding C, you can as well find E. Okay, so if you try to find the error vector that was introduced by the channel, it is equivalent to trying to find the code word that was sent. Why is that? Yeah, because R is equal to C plus E, I wrote that equation down. So you can either find C or you can find E. In fact, when you find C, you are also finding an estimate of the error that happened in the channel. Okay, so the question is, can you try and find this? How about finding this? Yeah, so what is the advantage of finding this, trying to find this? The prior probabilities are not all equally uniformly likely to be all the 2 power n possible vectors. Okay, so at outside it seems like it is a bad idea, because C, when there is only 2 power k possibilities, for E there are 2 power n possibilities, but it is heavily biased. For any reasonable P, it is very heavily biased. Okay, so the all 0 vector is most likely, and everything else is going to fall in likelihood. Okay, so after a particular weight, the probability of those things happening is very less. Okay, so you do not have to look at those things. Okay, so that is the thing that we will exploit in this syndrome decoder. Okay, try to find the error that happened as opposed to the code word that was transmitted, and exploit the probabilities in the channel, and that gives you a benefit. Okay, so that is the basic idea. But how do you find the E? Okay, it seems like a complicated problem, right? The code is given to you, you know the code, so you just go to the code book and look for C, that I seem to know, but how do I look for the possible E? Okay, so as it turns out, given an R, you do not have all the 2 power n possibilities for E. Yes or no? There will be only 2 power k, okay, because only 2 power k was transmitted. Given that you received a particular R, there should be only 2 power k possibilities for E. I mean, there was only 2 power k starting points. Given that you received anything, you can't have all possible error vectors, you can only go back to one of the code words. Only 2 power k possibilities exist. Okay, what is one way of describing the 2 power k possibilities? This is the way to describe it. Okay, what is a possible E? Possible error vectors. Okay, so you can say E belongs to R plus U such that U belongs to the code C. Okay, this is a way of describing the set of all possible error vectors. Okay, so I know R is C plus E, so E should be of the form R plus C for some code word C. So simply write it as R plus U, U belonging to the code C. This is a way of describing the possible error vectors. Okay, this is one way of doing it. It turns out there is an equivalent way which is really very powerful. Okay, so remember R is C plus E, right. C satisfies an equation using the parity check matrix. Okay, so if H is the parity check matrix, you know C satisfies H times C transpose is 0. Not only that, you also know that if there is an arbitrary vector x, if H times X transpose is 0, then X is in the code. If it is not 0, then it is not in the code, that also you know. Okay, so this is kind of like an if and only if, goes both ways. Okay, so if H times C transpose is not 0, then definitely C is not a code word, that vector is not a code word. Okay, so when you use that relationship here, you can multiply throughout by H. Okay, you can take H and multiply by the transpose of the left hand side and the transpose of the right hand side, and this equation becomes equivalent to H times R transpose equals H times E transpose. Okay. So now using this property, one can see that the set of all possible E is actually, let us say, the set of all E such that H times E transpose equals H times R transpose. Okay. Okay, so there are several ways of rigorously proving it. I do not want to write a big proof for these statements. It is quite easy to intuitively argue, and you can write down a proof for this. It is not too difficult. Okay.
But you can have two solutions, so either the all 0 or the other particular.
Yeah, it is a set. That's why I said E belongs to this set. Okay, so I'll come back to this. Okay, so what is this? This is actually, like you pointed out, is a system of linear equations. Okay, so notice H times R transpose is actually, what is the dimension of H times R transpose? See, H is n minus k cross n, R transpose is n cross 1. So H times R transpose is n minus k cross 1. Okay, and given R, you can eminently compute this vector at the receiver. Okay, very efficiently you can do it. It's not a big problem. Okay, so given H and R, you simply do H times R transpose. It will give you a vector n. Okay, so this vector is what is called the syndrome. Okay, usually it's denoted S. Okay, it is the syndrome. Okay. So what you have here, like it was pointed out, is a system of linear equations. How many equations do you have? N minus k equations. How many variables do you have? N variables. Okay, so the variables are here. So this is actually a system of linear equations. Okay, have n minus k equations and n variables. Okay, so clearly you can argue the rank is, if the rank is full, that there will be 2 power k solutions, and it is consistent with what we had before. Okay, so it is exactly the same. Okay, the set of all R plus u. So set of all R plus u, this is also size 2 power k, right? It all matches up. Okay, so you will get the same picture in various ways. Okay, all right. So all right, so I have a description for the possible error vectors, but now how do I use the knowledge that E is biased? Okay, so the question is, how do I solve this error vector, this equation, right? So essential idea in decoding is now solving. So decoding is the same as solving H times E transpose is S. Okay, what can I do when I get a particular R? When you get a particular R at the receiver, you can compute S equals H times R transpose, and then you can solve for H times E transpose is S, okay. You will get 2 par k solutions. Which solution will you pick?
Weight.
Okay, the solution with the least possible Hamming weight. Why is that? That is the definition of decoding, right. So then you pick the, so you get 2 par k solutions, you pick oh my god, this is becoming a rather large box. So let us just move the box. Pick lowest weight solution. Okay, and that will be your E hat, and then what will be your C hat? R plus E hat. Okay, so I will just leave it like this. So you know how to make C hat from here. If you want, you can do this. Add these two, and you will get C hat. Okay, so this is how a syndrome decoder will look. Okay, so it's optimal. It's clear that it's optimal. I am not doing anything suboptimal here. Okay, so this step is easy. The first step is easy. Computing the syndrome. Okay, so computing the syndrome is easy, and then this is called the syndrome equation. You can call it the syndrome equation if you like, right. Okay, so the crucial problem is solving the syndrome equation to get the least weight solution. Okay, I will get all possible solutions, that will be 2 par k. I will be stuck in the same old boat if I do all 2 par k. I want to somehow solve smartly for the least weight solution directly. Okay, so can I do that smartly is the question. Okay, so that is what gives you all these suboptimal decoders. Okay, so they try to smartly solve this equation for the least weight solution directly. Okay, all right. So this part is the tricky part. Okay, so it's usually difficult. There are various different solutions for it. Okay, but if you want to be optimal, okay, you might want to solve for the exact least weight solution. Okay, so that's when you will be optimal. So you do that. This is the same as optimal decoding. Okay, but I made this comment about 2 par n minus k. Where did 2 par n minus k come about? Okay,
syndrome that fall in the code word set should not,
okay.
should not count the E's that belong to C.
Well, that is not really, I mean if syndrome is 0 then E might belong to C. No? See, that is not the point. See, the point is if you make a table here, how big will the table have to be? That is the question, right. If ultimately I am thinking of a big table, right, for implementing this. Okay, so I have S coming out here, I have to produce E hat. How big will the table be? It will have 2 columns. What will it have in one column and what will it have in the other? Yes, okay, that is the important thing. It will have all possible syndromes in one column, and corresponding to each syndrome it will have an E hat. Okay, how many possibilities do I have here? 2 power n minus k possibilities. Remember, S is simply n minus k bits. Okay, so I have only 2 power n minus k possibilities for the number of syndromes. Okay, so each possible syndrome I go through, I get these error vectors. Okay, so the complexity is not as high as 2 power n, for instance. It becomes 2 power n minus k. If you want to simply implement the entire table, okay, you may not want to implement the table. If you want to smartly solve for the lowest weight solution, you can also do that. So that is where the suboptimal decoders come in. Okay, like I said, if n is 1000, k is 500, you still have a huge table to deal with here. Okay, so if you smartly want to solve for it, you can do that also. That is a suboptimal decoder. But if you want to be optimal, you need a table of size only 2 power n minus k as opposed to 2 power n in the other case. Okay, so that is where the simplification comes. Is that okay? All right. So how do you fill up this table? Technically, filling up each row is as complex as what you had before. You don't gain anything, right. So suppose I look at a particular S, what should I do to find out this E hat? I have to solve for H E transpose equals S, and that is 2 power k solutions. it seems like it's very complex, okay, but I should not be doing it, okay. Yeah, so I have to do something else. The reason why I have to do something else is I know my E hat is biased, okay. I have to do this operation in reverse. Instead of saying given an S, I will try to find an E hat, list out all the most probable E hats and find the S corresponding to it. That is very easy, okay. As you keep listing out all the possible E hats, see if you are covering all the possible S's. Once you have covered all the possible S, you can stop at that point, okay. So that is kind of a reverse way of building this table, and that is usually more efficient than trying to solve all of them, okay, and in every step you will get something. It is not like for each row you do not have to spend 2 per k. So overall the complexity remains at 2 per n minus k, that is what I am trying to say, okay. Alright, okay, so I have described this from in an abstract way, so we have to see examples, and when we see examples it will be a little bit more clear, okay. So let us go back to this example that we had. Hopefully I will be able to reproduce that same example, the 633 example. Okay, so here is the 633 example. For this, when we try to do this by hand, we saw that building the table for in the previous case needed 64 entries for all possible R, okay, 2 power 6, that is 64, that is a lot of entries, okay. But you will see if you do syndrome decoding, okay, the syndrome table, by the way this is called the syndrome table, I did not name it, it is called the syndrome table. Building the syndrome table on the other hand is not too hard, okay, at least for these cases when you do it by hand it is quite easy, okay. So let us see, let us try and build the syndrome table like I suggested, okay. So you have the syndrome S and the E hat. In fact it is so easy you can do it either way, okay. You can exhaust all possible E hats, or you can go syndrome by syndrome and try to find out what is the least weight E hat. Both of them you can try, okay. But the first thing you should write down is what? All 0 E hat, right, because that is the most probable one, and that will give you the syndrome 0, right. The next things you should try are error vectors of weight 1, okay. So you try them, for instance you do 1 0 0 0 0 0, you would get 1 0 0 here, then you do, okay, it is a piece of laborious writing down, we can do that. Okay, 0 1 1, okay. So how many syndromes have I covered? 7 different syndromes have already been covered, only one syndrome remains, okay, alright. So you have to keep looking for weight 2 error vectors, right. You have exhausted all the weight 1 error vectors, I got only 7 syndromes. Now I have to look for weight 2 error vectors. Now you can be a little bit smart, you can do this very easily. So you know the missing syndrome is what? 1 1 1. I want a weight 2 error vector which will give me H E hat equals 1 1 1. So how do I do that? So imagine here I am putting a vector here with 2 1s, okay, and when I multiply H times E hat I should get 1 1 1, okay. So how do I do that? Second and fourth, for instance, or first and last, or, okay. So now you are noticing an interesting thing, there are more than one possibility even for the least weight, okay. How do you, what will you do if you do that? If you have that, you can pick any one without losing anything in probability of error, okay. So what is happening is you are receiving a receive vector R, it is equidistant from multiple code words, okay. So it is happening for some crazy reasons, it can happen, you can end up, and you can go back to any one and you will not lose anything in probability of error. You can go back and see the computation, you see probability of error will remain the same. Okay. So, it will be optimal whatever choice you make here. Okay. So, let us do this choice for instance. Okay. So, this here you can put or 0 1 0 1 0 0 or what 0 0 1 0 1 0. Okay. Any one of these 3 E hats you can put there. Is that okay? Okay. So, there are a lot of useful notions that come out of thinking about the decoder as a syndrome decoder as opposed to searching for R to C. Okay, go ahead, there is a question.
How do you know that you will always get all possible values for S from the HR transpose?
Well, if it is full rank you will get, right, eventually you will get. If H is full rank, the question was how do you know that if I vary the E here I will get all possible 2 power n minus k. If H is full rank you have to get it, because there will be some columns which are linearly independent, you put all possible vectors there, eventually you will get it. So, you should get all possible 2 power n minus k. Okay. So, there are a lot of notions in this syndrome decoder. So, let us go back and look at this block diagram. Okay. So, this remember this is the block diagram, I have the table, you have to use it in this block diagram. Given an R, what should you do first? Should compute S equals HR transpose and then go to the table, look up the E hat and then XOR with the received R and you get C hat. Okay. So, this notion of figuring out the error really gives you this notion that you are correcting for an error vector. Okay. Right. There is an error vector that is introduced by the channel. I am trying to figure out based on the redundancy I have added in the code words, based on the gap I have between the code words, what was the error introduced by the channel and I am cancelling it. Okay. So, you are literally correcting for the errors introduced by the channel. I mean, it gives you a nice, I do not know, it is an intuitive way of thinking about it, it gives you that. Okay. From there you can make a list of what is called the correctable error vectors. Okay. So, if I have a syndrome decoder, if we have a syndrome decoder with a certain syndrome table, whatever it is that the error that was introduced by the channel, okay, the errors that I am declaring at the decoder will always be from the table only. Okay, right. I will always say this E hat will come from the table. Okay. So, these error vectors in the table are called the correctable error vectors. Any error vector outside of this table is not correctable. Okay. That is also an interesting statement. Okay. So, let me go back to the syndrome table. Okay. So, maybe I should spend a little bit more time with this correctable, incorrectable with this example before I go to the syndrome table. Okay. So, suppose in the actual transmission, okay, the error vector, the R that was received now, okay, so you remember the previous thing that I gave you. So, R that is received was let us say 1 1 1 1 1 1. Okay. What will be C hat? Okay. You can now answer this question without too much work, right? Can you answer this question? Let me see.
The error is the last one. Yeah, so 0 all 1 0.
Okay, the first thing you compute is what?
Oh, 0 4 1.
The syndrome. What is the syndrome corresponding to this R?
1 1.
Okay, so you have to do H times R transpose. Okay, so when you do that, what happens? You get 1 1 1. Okay, you can quickly do that. You will get 1 1 1. Then you go to this table and look up the E hat corresponding to that, and then XOR it with the R, and you get C hat to be 0 1 1 1 1 0. Now, this would have been very hard if you did the exhaustive search over all possible code words, right. So, you see it works out quite easily. Okay, so this simply picks out the last guy. Okay. Now comes a challenging question. I am going to ask a challenging question. can you give me any other R, okay, give me any other R which will give you the same syndrome. Give me one other R which will give me the 111000, right? So it's possible you can come up with any number of R's. How many other R's will there be? 2 power k, right? So it will be exactly 8. Find 8 other code words, receive vectors which will give you the same syndrome. Okay, all right. That's one thing. And the other thing is, see, so right now I am claiming my E hat was 100001. Okay, so when I declare this, what am I saying? I am saying this R was received when this code word was transmitted and the error vector 100001 was added to it, right? What is equally possible is you can have another code word, let us say for instance, I do not know, any other code word plus any other error vector, some other error vector, not any other, some other error vector which will give you the same R. Is it possible or not? Okay, for instance, just a silly case, you just pick the code word to be all 0, then what will be the error vector? All ones, you will get the R. Okay, all right. So we are only correcting errors with some probability. We are not saying for sure that this was the transmitted C hat. You can never say. If you can say, then there is no decoding problem, right? Some errors have happened. You are doing syndrome decoding and you are saying E hat was this, then C hat was this. That is correct only with some probability, but that probability is maximal, you know, it is maximal, but there could be some other code word. For instance, I mean just a trivial case is to take 000, but you can take any other code word. I mean you can take, let us say for instance 111, let us say 11, oh I should not start with 11, no, okay, maybe 110010, okay, and then 001101, this could be another error vector that got added, okay. But notice here the probability of this error vector is only what? It's p square into 1 minus p power 4. What is the probability of that error vector? P power 3 into 1 minus p power 3. That will be definitely smaller than the error vector that I picked. Okay, you can be sure that you are picking the most probable error vector, but there are definitely other code words and other error vectors with non-zero probability which could have given you the same R. So you can make errors even with the syndrome decoder. Okay, do not be under the assumption that you can never make errors. You will make errors. Okay. Okay, so that is where this notion of a correctable error vector is important. Okay, no matter what error vector actually happened, at the decoder you always declare that the error that happened was those errors that are in this table. Okay, you will never declare that the error that happened is outside this table, right? If some error outside this table occurred, you can never correct it. No, it occurs with a lower probability, but if it occurs, you cannot correct it. Okay, so that is the idea. Okay, so in the syndrome table, okay, what you have, the E hats you have are the, so here you have all syndromes. What you have here are the correctable error vectors. Okay. So what is easy to compute once you have the syndrome table is the probability of correct decision or probability of error. Okay, what is the probability of error? Probability that the E that occurred does not belong to the syndrome table. You can compute it as 1 minus probability that E belongs to the syndrome table. Okay, it is very easy to compute. Why is it easy? For instance, in this example, what is the probability that E belongs to the syndrome table? You have to simply compute the probability of all 0, 1, 0, 0, 0, 1, 0 and so on, and then add it up. Okay. So, what is the probability of the all 0 error vector? 1 minus p power 6. What is the probability of the remaining vectors? This guy is p into 1 minus p power 5. How many of them do we have? 6 of them do we have? 6 of them we have. So, let us say 6 p times 1 minus p raised to the power 5, and then what about the last guy? P squared into 1 minus p raised to the power 4. Okay. Okay, so these are interesting exercise problems, they are also interesting exam questions. Okay, so given a parity check matrix, come up with the syndrome table and then find the probability of error. Okay, so remember this is the lowest probability of error that you can ever get for this code. Okay, for the 633 code that we had, this is the lowest probability of error you can possibly get. You can never get better than that over a BSc P. Okay, and how do you compute that? That's the question. Okay, so somebody asks you, given a code, what is the lowest probability of error that you can find? How do you go about doing it? Find the syndrome table, find the correctable error vectors, simply find 1 minus probability that the error is in the syndrome table, you get the answer. Okay, it's a simple step 1-2 step procedure, but it can be done. Okay. So, I just did one example, so hopefully you can see quite easily how this example can be generalized. Okay, any other parity check matrix I have, you just repeat the same same thing, okay, one after the other you can do, and in your tutorial problems I do ask several questions like this, so you will see and you will practice some of these things. So, it is not a big deal. Okay. All right. So, one more property that you can now define given this notion of correctable error vectors is, okay, how many errors can you correct? Okay, that is the next notion. Okay, error correcting capability of a code. Okay, so that has a lot of definitions. Okay. So, suppose you have an NKD code, okay, this is usually denoted T. One can show that the error correcting capability T is D minus 1 by 2. I have not even defined it, I will tell you what I mean by it. Okay. When I say error correcting code capability is T, it means what? What does it mean? All error vectors of weight less than or equal to T are correctable. Okay, so it is very easy to define this once you know what it is. What is the set of correctable error vectors? Those error vectors that are in the syndrome table. Okay. All error vectors of weight less than or equal to T are correctable implies T is the error correcting capability. It is well defined, you do not have to worry about not being well defined, it is a very well defined quantity. Okay, so you can define it very precisely. Okay. Okay, so let us go back to this example. If you go back to this example, sorry, so you have a 6,3,3 code. From the computation you see T equals 1, right, 3 minus 1 by 2 you get 1. Okay. And clearly in the syndrome table you have all error vectors of weight 1 appearing. Okay. It is not 2 because there is only one error vector of weight 2 that is appearing here, there are several more of them that have not appeared. Okay. So, that is the idea of error correcting capability. Okay. There is also a useful way of visualizing error correcting capability, which is once again interesting. So, once again we will do this picture which represents F2n, all these dots which are n bit vectors, and what are the stars? Stars are the code words. Okay. So, you have transmitted a particular code word, when you add errors to it, what is happening? You are moving away from the code word. If the error was of weight 0, then you will be at the code word itself. If the error was of weight 1, you will be within the Hamming ball of radius 1. If the error was of weight 2, you will be within the Hamming ball of radius 2, etc., etc. Now, if you draw Hamming balls of radius t, what will happen? They will not cause any intersection. Okay, there will be no intersection for Hamming balls of radius t. Okay, so t is d minus 1 by 2. Okay, so this is radius t. Okay, so we saw this idea before in the Hamming bound. A very similar idea is happening here. So, if at all only t or fewer errors are introduced, you should be definitely able to correct them, because the minimum distance will be to a unique code word. There will be no confusion. Okay, you will never go farther away from the transmitted code word, you will be able to correct them, there is no problem. That is another interpretation for this t. Okay, so that is the error correcting capability of a code. Any questions? Everybody totally exhausted? Still have 38 minutes to go, so it is a long way ahead. Okay, all right. So now you see why d equals 3 and d equals 4 are not really making a significant difference. You see, if you have both d equals 3 and d equals 4, what happens? Your t is still 1, right, and this will continue. If you have d is 5 and 6, then t becomes 2. If you have 7 and 8, t equals 3. Okay. So, usually that is why people will worry about d that is odd only. Okay. So, in fact, usually it is very common to take d to be 2t plus 1 and then have t as 1, 2, 3, etc. Okay. So, this is what you usually want. Okay. So, this will give you a t error correcting code. Okay. Right. From our designs so far, we have only one error correcting codes. We are not able to design a 2 error correcting code. Okay. So, you have to go to d equals 5 for that. Okay. And you will see it is a bit non trivial. Binary alone is not so easy. Ultimately, you can do it, it is not impossible, but it is a little bit more difficult and complicated. Once you go to non binary fields, you will see constructions become much easier. Okay. So, that is the reason why people move to other fields and think of other interesting constructions. Okay. So, I think this kind of brings us to the end of binary codes and all that I wanted to say. We are going to move towards finite fields. So, in case there are any questions or comments or anything that is disturbing you, it is a good time to ask. People are okay, you have reloaded all your batteries, recharged. Okay, so I think this is a good place to stop as far as binary codes are concerned. Okay, so if you want a quick recap, its binary codes are k-dimensional subspaces of F2n. You have the generator matrix which describes the binary codes. You also have the parity check matrix. Okay, then you have minimum distance, which is a crucial property which controls error correcting capability. Minimum distance is connected to the parity check matrix. In fact, you design parity check matrices with a certain minimum distance. Then the parity check matrix also plays a key role in the decoder. Okay, it gives you a nice implementation for the decoder. It gives you a feel for how the decoder works, etc., etc. Okay, so that's that is where we are going to stop and move towards finite fields. Okay, so before I move to finite fields, a couple of quick background material, so to speak. I mean, it's not really. I mean, I won't do all the background. I will assume some of the background you know already, but some things which you might have forgotten, or you may not have learnt it in the careful way, which sometimes it can come back to hurt you. Okay, so one of the things I see people are confused about is usually division. Okay, so how do you describe division? So division with remainder is what I am talking about. So if you have two numbers a and b, okay, when I divide b by a, what am I doing? Okay, so many descriptions come about. The way that's most useful, at least in this course, is to think of division of b by a as finding two other numbers q and r such that b equals aq plus r, and then r is between 0 and a minus 1. Okay, so that's the crucial way in which you have to think about division. Okay, so division with remainder, when you divide b by a, you are basically finding a quotient and a remainder. B equals qa plus r. Okay, usually q, I mean all these are integers. Okay, so I am not said anything about what these things are. Everything is an integer. You are trying to find an integer q and r, and there is a restriction on r. R has to be between 0 and a minus 1. Okay, it's strictly less than a and can be 0 also. Goodness, saying all. Sorry, but how can you write without your palm touching, man? Like this? I'm not going to write like that. All kinds of things are open. I think that's also a problem. Yeah, I think hiding the taskbar is a good idea. That's something I should try later. Okay. All right. So this is the way to think about division. Okay. So when do you say a divides b? If r is 0, we say a divides b. Divides b. Okay, so this is usually written as this notation. Okay, so this is the same as this notation. Okay, so this is just shorthand for a divides b. Okay, so there is a similar division for polynomials also. Okay, so it's a little bit more involved. It's also this very similar, but a little bit different. Okay, so if you have two polynomials b of x and a of x, when you divide a of x, b of x by a of x, what are you actually doing? You are finding two other polynomials. One is called the quotient polynomial q of x, other is called the remainder polynomial r of x. And what is the condition that is true there? Yeah. Okay, degree of r of x is degree of a of x. Okay, so that's the idea. Once again, when do you say a of x divides b of x? R has to be equal to 0. Okay, so once again the same condition true. It's true. Okay. All right. So next there is one more quantity called the GCD. Okay, the greatest common divisor. We may not use it too much, but I'm just letting you know because sometimes I might need it somewhere, and then I should not be lost somewhere. Okay, so GCD is basically the greatest common divisor of a and b. Okay, so how do you define GCD of a and b? Okay, it's usually denoted like this. Okay, it is GCD of a and b is what?
Integer which divides both a and b.
D such that no other.
Okay.
It's the greatest number which divides a and b.
The LCM of a and b divided by.
So it's such that a comma b is what, let us say greater than D whenever what, D divides A and D divides B. Also then what should happen, A comma B should divide A and A comma B should divide B. Okay. In fact, see, this is the definition of the greatest common divisor, right. So, it is a divisor of both A and B, common divisor, and then it is the greatest such common divisor. If you have any other common divisor, this is going to be greater than that. In fact, you can use this definition and the division property as in division algorithm that exists in the integers to show that in fact this is true. What is true? It will also divide, no, I think it is the other way around, I am sorry, T will divide A comma B, but anyway that is not too crucial here, but these are equivalent to D dividing, I am sorry, okay, yeah, if you want I will put K, it is okay, it does not matter, okay, D dividing A comma B. Okay, so think about how you might want to prove it in case if you want a simple problem and this. So this is one such thing. And also another very interesting property which is called it is a very famous algorithm for finding GCD. You can use that algorithm to also do that. This Euclid's algorithm. Euclid's algorithm gives you a way to do the following. It turns out the GCD of A comma B can be written as R times A plus S times B, where R and S are also integers. Okay, so there is a linear combination of A and B which will give you the GCD of A and B. Okay, so this is also an interesting result. You do Euclid's algorithm, for instance, how do you find GCD? You start with B, divide A, take the remainder, then push A and R as the divisor and the dividend, okay, and then you proceed like that. So you just undo the Euclid's algorithm, you will get this R and S. It is not easy. So at every stage you are only doing linear combinations, right, with the quotient. It is very easy to see that. So you will get this formula. So in particular, if A and B are relatively prime, when do you say A and B are relatively prime? Okay, if A B equal to 1, then you say A and B are relatively prime. What does relatively prime mean? They have no common factors. Okay. Okay. So what should happen if A and B are relatively prime? There should be a linear combination of A and B which gives you 1. Okay, so that is an interesting property. So all these things are true also for polynomials. Okay, if A of x and B of x are polynomials with coefficients from some field, okay, so they have to have coefficients from some field, otherwise nothing is true. Coefficients should come from some field, usually like real numbers or something like that, or rational numbers. Then all these things are true. You have also GCD for polynomials. Then you also have the notion of polynomials being relatively prime. Then you also have the notion of the GCD being able to be, when you can write it as a linear combination of A and B. Okay. So I know I am saying this is all real quick, but we won't really use all of this, but in case you have to, the reason why I am giving you this is in case you have to prove some of these properties, you will have to use these results. Okay. Some of the properties that I am going to write down, maybe you might have to use these results, and I will quickly point to the proof. I won't do many of the proofs in detail, but I will quickly point to the proof and I will mention some pointers like this. Let's say you use these properties and you can prove it. Okay. Just so that we are on the same page, I have to write this down. Also, some of the formulas that I want to write will involve things like GCD. Okay. So it is good to know what the GCD is and how it is related to the numbers. Okay. So if any of this is really troubling you, don't worry about it too much. When we actually come to it, I will explain it in more detail, but you won't need to know much more beyond this. Okay. One way of finding GCD is what you just said, do the prime factorization and then pick out the largest power, the smallest power of all the common prime factors. That will give you the GCD. That is how we find it. Prime factorization is not easy, right. So Euclid's algorithm is an easy way of finding GCD. It can be found very easily using Euclid's algorithm. How many of you remember Euclid's algorithm at all? Maybe a little bit. Okay. I am sure it was taught to me in school, but just not that familiar. Okay. All right. So these are some things that will be needed. So let us just jump into the definition, and as and when we need it, we will maybe come back to this or maybe not. Okay. All right. So we are going to see finite fields. I wrote down the definition for fields before. I want to quickly remind you what the definition is. So, definition of a field, okay. So, you have a set F with 2 binary operations but once again, why are we going to finite fields? What was the logical progression that took me to finite fields? Yeah, we want to design codes with d equals 5 and higher, and the only construction that people have so far which is nice to describe is uses these finite field ideas. Okay, so that's one of the reasons we are going, but even otherwise finite fields have so many other applications in so many related areas, it's good for you to know them. Okay, so don't think that these are very abstract objects used only in coding theory, it's used everywhere. Okay, so not 2 binary operations which we will call plus and dot. Plus we will call as addition, dot we will call as multiplication. We want the following conditions, right? I will write it only sketchily, I think, because the last time I gave you very precise definition, so just quickly writing it. F comma of plus should be a abelian group, okay. F star, okay, what is F star? So abelian group means clearly it should have an identity element, okay. So 0 we will take as identity of additive identity, okay. So it's just a notation for the additive identity in F, okay. We will call it as 0, okay. F star, which is F minus 0 comma dot, should also be an abelian group, okay, and 1 will be termed as the identity element of the multiplicative group, okay. And there are some conditions. I mean, for instance, multiplication has to distribute over addition, okay. So such things should be true. A dot b plus c should be the same as ab plus ac, etc., etc. Okay, so all these are other conditions that you can put. I think this is the only other condition. I don't think there is anything else. They put etc., etc. So maybe I will remove it. This is also, this should be there. Okay, so multiplication should distribute over addition. I think this gives you a field. Okay, so basically from a very high level, field is something where you have a set of elements and you can add 2 elements. You can also subtract them. Okay, in a group you can add and subtract, right? Or you can multiply and divide. So in the field you should be able to do all 4. You should be able to add, subtract, multiply, divide. Divide by 0 is not needed. Okay, so it just extends your notion of a field to something more abstract. Okay, so it has some elements. If you want to be very definite, you can think of the rational field. The rational numbers are a nice field that you can imagine in your head, or you can think of the binary field F2. Okay, so one of the first non-trivial examples, which is also finite, is this Fp. P is prime. Okay, what is Fp? 0, 1, 2, so on till p minus 1. Okay, addition and multiplication are basically integer addition, integer multiplication modulo p. Okay. Okay, so basic, if you let the size of f be infinite, you can get a wide variety of fields. All kinds of fields are possible. Okay, so there's lots of interesting stuff there also. But if you restrict f to have a finite number of elements, the fact that it needs to have a finite number of elements and it has to be closed under 2 different operations that interact with each other with distributive sense is a serious limiting thing. Okay, you do not have too many finite fields. Finite fields have a very precise structure. Okay, so we will see it soon enough, but Fp is one such example. Okay, so here is one such example, and you see there are too many conditions, right? You have to be able to add them, and still you should not leave the field. And every element should have a inverse also in the same field. Okay, all these things are fairly serious limitation. It doesn't seem very obvious. I mean, how to pick out fields, etc. Okay, so this, for instance, is a field. Okay, what are the various properties that are easy to verify? If you want to verify some of these properties, which one is easy to verify? F comma plus being an abelian group is a very easy thing to verify. Okay, so you add any 2, closure is definitely there. Inverse, how do you find the inverse?
P is small, then
Subtract if it is
If you have
negative.
any I, what is the inverse of that?
that
P
might be
minus
small.
P minus I.
P inverse, right? Why will it not be the inverse? You can explicitly write down the
Inverse
additive inverses, no problem. So abelian group for the plus additive group is easy. Okay. What is slightly non-trivial is f star with dot modulo p being an abelian group. It's a little bit non-trivial. Okay. Once again, closure is not a problem, identity is not a problem, inverse is the only thing which is a bit of a sticking issue. You can't directly see that every element has a multiplicative inverse. Okay. So it's not very obvious. Okay. Maybe it is obvious to some, but it's not very obvious. There are some non-trivial number theory results, very simple ones, which you'll see in the first chapter of every number theory book, which will give you the fact that everything has a multiplicative inverse also. Okay. But if you haven't studied it, it seems quite fantastic that for any prime number, right, any other number a less than that prime number, I have an a inverse which when multiplied modulo p will give me 1. Okay. So it's not very obvious, it's a difficult thing to prove. For instance, for 5, right, if I take p equals 5, what is the inverse of 2, multiplicative inverse of 2? 3, right. So suppose I take a large prime, give me a large prime, I don't know, it's just difficult to find. Let's say 31, okay, it's not that large, it's prime. What is the inverse of 25? It's not easy, right, not easy. So it just becomes a little bit more difficult to visualize, but the fact that it exists can be shown quite easily. Maybe we will see a quick proof, we will come to that later. Okay. The distributive property is also very easy. Okay. It just comes from integer addition and integer multiplication, right. Integer addition and integer multiplication has the distributive property. So when you do the same thing modulo p, you also have the integer property, there is no problem with that. Modulo does not change anything with addition and multiplication. Okay. You can do all kinds of stuff, so there is no problem there. Okay. So the only non-trivial thing is to show what? Yeah, so that is the only thing I want to show. So let me see if there is a quick proof here which I can easily repeat for you. Okay, so here's a simple enough proof which I think is which I think will work. Okay, suppose I take some element a. Suppose you take a in Fp and a is non-zero. Okay, it's important. Now look at this following list of elements. Okay, the list of elements I'm going to look at are a into 1, a dot 2, a dot 3, so on till a dot p minus 1. Okay, when I say dot, what do I mean? It's multiplication modulo p. Okay, so my claim is there is no repetition in this list. Okay, remember there is closure, so all of these things belong to what? Fp star, they are from 1 to p minus 1, you won't get anything else. But my claim is there is no repetition in this. Once I show that there is no repetition in this, what has to be true? One of them should be equal to 1, and that shows my inverse. But how do I prove that there is no repetition in this? Yeah, you can show that. Okay, for instance, if a times I equals a times j mod p, what should happen? A times I minus j or j minus I, depending on what is larger, should be 0 mod p, which means p has 2 factors, okay, but p is prime, cannot have a factor. Is that a good proof? Everybody is happy? Okay. Think about it. Okay, so it's an interesting proof. Okay, so that's how you prove it. Okay, so notice the proof is not constructive, it's not explicit. It doesn't tell you for a what is the multiplicative inverse. In fact, there is an explicit way of writing it down also, but anyway, it doesn't matter. So it doesn't give you what is it explicitly, but implicitly it says it should exist. Okay, I know I didn't write down all the steps. I don't mean to write down all the steps. You please fill in if you feel like it. Okay, so it's up to you. It's not important to know all the steps of the proof, at least in coding, but you should know how the proof is built. Okay, is it okay? Any questions on this proof? No. All right. So it won't work if p is not prime. You see that p is not prime, you can eminently have a times j minus I equal to 0 mod n. Okay, there is no problem. Since p is prime, it works. Is that okay? Okay. Alright, so this is a finite field. Okay, so you have one finite field. Okay, of course there are you might say there are infinite number of primes, so there should be an infinite number of finite fields. Yeah, there are infinite number, but quite few, no, number of primes between 0 and 1 n are like log n, so it's quite a few, very few number of primes in the list. Okay. All right, so what else do I have to say? Okay. So the next thing that is a little bit interesting is okay, polynomials over a field. Okay, I want to say a few more things formally about these things, and then we'll proceed. Okay. So if you have a field f, okay, think of it as some finite field for now, think of it as some fp. Okay. We will define first, let us define okay, we will define the set of polynomials over f. Okay. Okay, which is denoted f with square bracket x as the set of basically polynomials. So what is polynomials? A0 plus a1x, x is the variable, a2x squared plus so on till some an x power n. Okay, only a finite number of terms. Okay, so n is some finite number. These ai's belong to the field f. Okay, so these are also called polynomials with coefficients from f. Okay. Okay, all of you knew this, right? There is no problem. So polynomials are finite number of terms of this form, a0 plus a1x plus a2x square, so on. Okay. So of course what I wrote down about division is very, very important. Okay, so if you have division is the most crucial property for polynomials, which we will use quite extensively. Okay, so if you have two polynomials a of x and b of x, okay, belonging to fx, okay, they should come from the same fx. Okay, otherwise division will not make any sense. How will you do polynomial division? Okay, you know how, you remember the long division method, right? So don't tell me you forgot that. Okay, I am not going to do the long division method for you. How do you do the long division method for polynomial? So when you do b of x divide b of x, let us say divide b of x by a of x. When you do that, what do? You put b of x inside the, you write something like this, you must remember this, no? You put b of x here. I mean, everybody is laughing, I do not know, but I was surprised that some people did not know this. You put b of x here, a of x here, and then what do you put here? You put the coefficient needed to cancel the largest degree term, but see, you have to remember these coefficients are now coming from the finite field. Okay, so you have to pick a suitable term. Okay, so you have to pick a suitable term which will be the coefficient of b divided by the coefficient of a that you want. Okay, the largest coefficient. So everything is in the finite field now. Okay, so the division is a little bit more complicated. It is not as simple as just putting b by a. Rational field is what you must have been used to, and you simply write b by a there, right? You can't do that here. Okay, so you have to go to the finite field every time you want to divide and cancel the first term. Okay, but other than that, the long division steps are exactly the same as the long division you learnt in school. There is no difference. Okay, you do that. Finally, what you have here is the quotient, and after a lot of steps, what you have at the end when the degree goes below a is the remainder. When you can't cancel anymore, you get the remainder. Okay, so that is the idea. That quotient and that remainder can be written in this form. Those are the unique q of x and r of x such that, is it unique? It is unique if you say degree of r of x is between 0 and degree of a. Okay, so you write that formula, right? So b of x is a of x into q of x plus r of x. Okay, so it is the same division, it is nothing really different, okay, it is the exact same division that you have learned from your school, except that the coefficients are from the field. Okay, so you will have to do division in the field. If it is a finite field, you have to do division modulo that p. For instance, if it is fp, you have to do division modulo that fp. Okay, so it is a little bit different, the division will work different from your intuition. Okay, so this division, and then I actually have an example worked out. Maybe I should do that example, it is a good idea to do that example. Okay. So here is an example, here is how you divide, for instance, x power 4 plus 2 x squared plus x plus 1 by x squared plus x plus 1. This division, let us say, is in f5 of x. Okay, I am imagining that these polynomials are in f5x, they could also be in f7x or f11x or anything, I am just taking f5, well, it is a little bit easier. Okay. The first term is easy. Why is the first term easy? Well, it is just 1, so you just put x squared for the quotient, then what do you put here below this? X power 4 plus x power 3 plus x squared, and then you add these two things. When you add these two things, what happens? X power 3 remains. Okay, I am writing it a little bit non-standard, I mean usually you will leave a gap here, right, so that you can fill in the x power 3, but it is okay. 3x squared plus, oh I should subtract, you are right, I am sorry, 4x cubed plus x squared. Okay, so you have to subtract, say I am still in the binary mode, so I am just adding. Okay, so when you go to f5, you have to definitely subtract, you cannot add, you will not get anything. Okay, so plus 1, right, yeah, 4x cubed plus x squared plus x plus 1, then what do you put here? (4x), is that okay? Then you get what here? 4x power 3 plus 4x squared plus 4x. You do that, what do you get? You get 2x squared plus 2x plus 1, is that right? Okay, this will cancel, 1 minus 4 is 2 in f5. Okay, it is minus 3 mod 5 is 2. Okay, again 1 minus 4 is minus 3, mod 5 is 2. So remember this is minus, okay, do not do plus. Okay, I think if you are doing plus you will get 0 already. Okay, do minus, okay, and then you put the last term which is 2 and you get 2x squared plus 2x plus 2, and you have to again do a minus, so you get 4. Okay, so you can verify this formula, you can verify my formula, right, b of x is q of x times a of x plus 4. Okay, so this is the division, and I mean the other point of doing this example is that it is not really that hard. Okay, it is just written in the notation and all that, you get a little bit confused, but you may not have known that result, that b of x is equal to q of x, a of x plus r of x, when degree of r is restricted to be between 0 and less than degree of a, you get unique q of x and r of x. So that is a good thing to know. Okay, so division is fine, and then 0 is fine. Okay, okay, so then the next thing is zeros of a polynomial. Okay, so that is also important. Okay, what are zeros of f of x? Okay, suppose, so it is very typical to denote as f of x. Suppose you have f of x belonging to, or let us say a of x belonging to fx. Okay, what do I mean by this? A of x is a polynomial with coefficients from f, that is what I mean. Okay, so it is just written in that notation, there is no need to panic over that notation, just writing a of x is a polynomial with coefficients from f. Okay, okay. So one needs to be a little bit careful here when you try to find roots for a of x. When do you say x naught is a root of a? Okay, if a of x naught is 0, x naught is said to be a root or 0 of a of x. Okay, so one of those two terms. Okay, one very interesting result which is true is a of x naught is 0 implies something about factoring a of x. Okay, this is true if and only if a of x can be written as x minus x naught times b of x. Okay. Okay, and then degree of b of x will clearly be 1 less than the degree of f of x. Okay. So this is one way to factor a polynomial. Okay, so our goal is to factor a polynomial. If you want to factor a polynomial, one way is to find a 0 or root of it. Okay. Now remember, my a has coefficients from f. So where will I look for roots? In f, right? In f is what you would immediately think. Okay. But remember, several times when you have real polynomials with real coefficients, or let us say polynomials with even rational coefficients, where do you look for the roots? Not just in rational, right? You look for in rational. If you can't find rational, then where do you go? You go to the real field, right? So for instance, if I have a equation of the form x squared minus 2, if a of x is x squared minus 2 and it belongs to qx, by the way, q is a notation for rational numbers. Rational numbers, they form a field. Okay. So here there is no root in the rationals. Can you show that? Sure, you can show that. Okay. So there is no roots on the rational, there is no square root of 2 in rationals. You can show root 2 is not rational. Okay. So you can easily, it can be shown. So there is no roots in the rational. So what do? You go to the real numbers, and in the real numbers there is a root. Okay. Square root of 2 is a root in the real numbers. There can be also other polynomials of the form, say x squared plus 2 or plus 1, which again belongs to qx. For this you will not have solutions even in the reals. Okay. You have to go to the complex fields. So it turns out when you want to find roots for a polynomial over fx, you can either look for roots in f or roots in fields that contain f as a subfield. Okay. So if any field contains f, then you can even look at that. Okay. So we haven't talked much about these things, we will come to it soon enough, but hopefully your intuition with the rational field and the real field and the complex field is giving you that idea. Okay. You can either look for roots in your field, and if you do not find roots in your field, it is not factorable in that field, but then what can I do? I can go to a larger field which contains my field as a subfield, and then in that larger field I might find roots. Okay. So it turns out for polynomials with rational coefficients, which is the largest field, you have to go to complexes. So you can show that interesting result, it is called the fundamental theorem of algebra. So any polynomial has a root in the complex field. Okay. So any polynomial you can keep on factoring till you get all possible factors in the complex field. So you do not have to go beyond complex field if you have rational coefficients, and in fact any polynomial with complex coefficients also has a root in the complex field. So it is enough, it is closed, so at that point it ends. Okay. You do not have to search beyond that. Such things will not be true in finite fields. Okay. You will have to go on and on and on and on. Eventually you can factor, but you will have to go to larger and larger fields. There is no saying when you can stop. That is a bit of a different result in finite fields. Okay. So that is something you can expect coming in. Okay. And factorization will play a fairly important role both in the construction as well as in the codes that we construct. Okay. So factoring a polynomial over field is fairly important. Okay. So now having said that, the next thing is, if p is small, okay, and if f is some fp, okay, and if p is very small, let us say 5 or 7 or something, and if I know there is a root, factoring it is quite easy. Why? All I have to do is this, right? I have to simply substitute all the possibilities to find the 0. Okay. Finding the root of a polynomial in the real line is a bit more difficult. Okay. For quadratic you can do it very easily. For cubic also there are known formulas. For quartic there are known formulas, but from 5 onwards there is no known formula. Okay. But in the finite field that problem does not exist because you have only finite number of elements. So you simply substitute one after the other, you will find out which one is the 0. Okay. So it is a little bit simpler, but it is also non-trivial in some ways. Okay. So we will stop at this point. If some of these things shocked you, or you want to go back and read about polynomials and numbers and all that, there are several good books. I would suggest books by Rosen for number theory, okay, Kenneth Rosen. lots of reasonable books, they are very accessible at all levels. Okay, so we will stop here.